Hi everyone. In this video, I am going to explain about contiguous memory allocation, which is also called as multiple partition method, also called as variable sized multiple partition method. Okay, so don't worry about these things. We will discuss. Okay, you will came to know that what is the meaning of this multiple partition, variable size, all those things you came to know. But see, we know that what in my many videos I told, we user always we store anything. It may be any file, it may be any movies file, or it may be some Word document, it may be some apps, whatever. We are storing, user is always storing secondary memory. This is my backing store. Backing store, secondary memory, all are same thing. So okay, we stored here. And whenever we are want to execute anything, that program should be in the main memory, because CPU can take only from the main memory, CPU never take from the secondary memory. So whichever the program we want to execute, that we need to move from secondary memory to the main memory. So that's why see, whenever we double click on anything, when we open or when we are running, executing, our processor takes some time to buffering, right? So that means it is taking time to move the files from the secondary memory to the main memory. Okay, and then once the programs are brought into the main memory, then our CPU can go here, take one instruction, bring here, execute, again go to the main memory, take the next instruction, bring here, execute. So like this it will do. Okay, so this is once the program is done, again that program is again moved out from the main memory into secondary memory. So this movement of programs between the main memory and the secondary memory is done by our operating system, called memory manager. So in order to move the programs in between secondary memory and the main memory, we have four methods are there. One is swapping, contiguous memory allocation, paging, segmentation. We have discussed already swapping. Okay, now let us see what you mean by contiguous memory allocation. So that is what for today's topic. Okay, so now we know that what our program. So whenever our program, so initially I stored the program in what? In my secondary memory. At that time it will be in the new state. Whenever a program wants to execute, it should be in the what? Main memory. But so whenever our program wants to execute, that will be in what? Ready state. Okay, so ready state means this program is ready to execute. It is waiting for some what? Main memory allocation. The programs which are waiting for main memory allocation will be one queue. Okay, one queue. Okay. So this is called input queue. Input queue means here whichever the programs which are waiting for main memory allocation, that will be in the input queue. So once the programs are ready and once they are brought into the main memory, then they are ready, and at that time, so see, once the program is created, it will be in the input queue and it will be in the new state. Once the programs are brought into the main memory, they are in the ready state. That means they are ready to execute. They are in the main memory. Ready means they are waiting for CPU time. Once they are ready, once CPU will take that instruction, now it is what? Running state. Now it is running state. Running means the instructions are being executing by what? Our CPU. Whenever our processor executing, after some time, every program needs some IO device services. Whenever our running program requests for some input-output devices, assume if that input-output devices are free, immediately it will given to the process, it will use us. Suppose if the input or requested IO devices are not free, at that time that running processors has to wait for that IO devices to become free. Okay, at that time running process go to waiting state. Okay, so this we know. That means when the process go from running state to waiting state, whenever our processors want some IO devices and that IO devices are right now it is not available, and because it is already allocated to some other process. So that's why it is in the waiting. Okay, so waiting. That we know that. Okay, now the input queue. Now this is not process state transition diagram also we know that. Now let us take my main memory. See, main memory. So initially main memory means I am talking about what? RAM, random access memory only. Initially my RAM is, see, assume my system is switched off. turned off. Okay, now nothing is there. Now whenever we switched on, the first program what we brought into the second main memory is our operating system and some other system software. Okay, so this is what the kernel space will call. But that means almost 50% of the main memory space is occupied by operating system and system software. Now remaining portion is available for user. So we'll call this user space. That means here in this space we can load our user programs. Whatever we want to run, whichever the apps or whichever the file we want to open, that should be done here. Okay. So now in this method we consider the entire main memory as a one big whole or one big partition. Now out of this one big partition, right now I'm having two partitions. In the one partition I'm having the operating system and system software. In another one is a free partition. Okay, this entire one partition. Here instead of calling partition, we call it as whole. Okay, so now instead of partition, I'm using the word whole. Now our main memory consisting of two holes. One hole is occupied, another one big hole is a free hole or free partition. Now after operating system is loaded, see whenever we on the system, operating system will be loaded. Once operating system is loaded, then we can perform our task. So now assume we brought some process. Okay. Now whenever we brought some process, now I'm having, see now I'm talking about only this one. I'm not talking about this kernel space. I'm talking only about the user space. So I'm having one bigger partition. When I brought one process, assume I brought say one process, say for example PA, process A. So now this is of one part. Now among the user space, among two partition. Out of two partition, this is occupied hole or occupied hole. This is my free hole. Okay. Now similarly, after some time, assume I brought one more. I executed one more. So again, that also I brought from secondary memory to the main memory. Assume I brought our process 1. Okay. Now I'm having in the user space 1, 2, 3 holes. Out of 3 holes, 2 holes are occupied and 1 hole is what? Free. Now assume again after some time, again I opened one more file. So assume that is say for example PX. Now I'm having in the user space how many holes? 1, 2, 3, 4. 4 holes are there. Out of 4 holes, 3 holes are occupied, 1 hole is free. Okay, one more. Now here that means why this called as a contiguous memory location. Now whichever the processor programs waiting for the main memory location in the input queue, they are loaded into the main memory in a contiguous. See, PX is continuous. Once started here up to here, done. So PX is not scattered, not divided into different partitions. Okay, so now assume PX size. PX size is for example say 180 KB. Size of this process 180 KB and assume process P1 is say for example 360 KB and my another process PA is for example 220 KB. Assume these are. Now assume my free hole. This is my free hole. Assume my free hole. The size of this free hole is say for example say 200 KB. So out of 4 holes, 1, 2, 3, 4 holes, 3 holes are occupied and their size is this one. And they are in contiguous. Hence it is called contiguous memory location. And where we call multiple partition, see earlier I am having one hole and this user space, 2 bigger holes. Out of 2 bigger holes, this one user, the bigger one larger user hole, we have divided into multiple partitions. Hence it is called multiple part. That is in the user space I am having 1, 2, 3, 4. 4 partitions, multiple. See in this example I took 4, not always 4. It may be sometimes what 5, 6, 8, whatever it may be. That depending upon the what type of programs or what size of programs user is bringing. Okay, so we call it as a multiple partition. Hope you people know why it is also called as multiple partition. Why it is called contiguous memory? Here all processes are in contiguous. Okay, they are not non-contiguous, or they are not scattered, or they are not divided. Here some part of PA, here some part of PA, not like that. It is contiguous. Hence it is called contiguous. It is called multiple partition because our one bigger whole we divided into multiple partition, where each partition is in one process. This one here, in each partition one process. So in this partition one process, like this in every partition one process. Now out of 4 partition, 3 partition are occupied, 1 partition is free. Assume after some time we brought one more process, for example say PY, and it is of size 200 KB. Now now the main memory is full now. Assume for example now the main memory is full. So now I am having totally 5 partitions or 5 holes, one bigger hole, operating system and system software. This is kernel space. We are not talking about. We are talking about only the user space. User space consisting of 4 holes. Out of 4 holes, all 4 holes are occupied. And see, like in this example 4, always it is not 4, sometimes it's 5, 6, 7, 8, 9, whatever it may be. So that means we have multiple processes are there. But in one partition, one process, so we can have one process in one partition. So multiple partition, multiple process. How many partitions are there? That many number of process. So the degree of multi-programming. Okay. So now, so hence it is also called as multiple partition method. And why it is called variable sized multiple partition method? See, this partition size is 220 KB, this partition size is 360 KB, this partition is 180 KB, and this hole is of 200 KB. So each hole is of different size. That means sizes keep changing, varying. So hence it is also called as variable sized multiple partition method. Hope you people understood. Now, assume right now my all holes are occupied. My all partitions are occupied. See, whole partition both are same. So now assume, now I want to bring another program from the input queue or from the secondary memory into the main memory. But there are no holes are free now. Now what to do? Now again, see, whenever any one process operation is completed, we need to move that out. Assume for example, process PX completes. Process PX completes. Now process PX completes, we close that app. So now that process is not in the main memory now. Now out of these 4 holes, 3 holes are occupied. 3 holes are occupied. 1 is free hole. Our operating system maintains one table saying that how many partitions are there or how many holes are there, out of how many holes, which are the free holes, and what is the size of the hole. Because whenever we are bringing the new program from the secondary memory into the main memory, we need to check which are the partitions are free. Not only which are the partitions are free, we need to check whether that new program can be fit in this free hole or not. Suppose for example, assume I want to bring a new one more program. Assume that size is say 210 KB. Now, so now here out of 4 holes I am having only 1 free hole. So it is not possible to bring 210K into 180 kilobytes. Okay, so it's not possible. So whenever we want to move a new program from the input queue into the main memory, we need to check which are the holes are free. First thing. Second one, so to which hole we can, that is size of the each free hole and the size of the program which we are bringing. Suppose if the size of the program is less than or equal to that free hole size, then only we can brought, otherwise it's not possible to brought. So in this example, 210 kilobytes, so this program cannot be brought in this free hole because the size is less 180 kilobytes. So lesser than. Okay, this is what we need to look for. Now, assume after some time again, I close process P1 also, I close process PA also, okay, and I close PY also. All processes I close. Now my complete user space is free. That means now I am having 1, 2, 3, 4. 4 holes are free. All the 4 partitions are free. Now assume I want to bring this 210K new program into any one of the partition. Now, which partition I can say, see, this 210K, is it this partition cannot fit in this 180 kilobytes free partition, but it can fit in 360 and 220. Where to allocate? So now the question is, whenever we want to bring a new program into the free hole, which free hole we need to select? In order to select the free hole, we have three selection methods. They are best fit, first fit, and lastly worst fit. That means now I need to check in which free hole the new program can fit. To select the free hole or free partition, so we need to have three selection criteria: first fit, best fit, worst fit. Now let us see one by one. First fit. Now in the first fit, what we will do? In the first fit, I keep checking the free holes. Whenever I find the free hole which is large enough to fit, so I'll stop there and I'll fit. For example, now in this case, this is a 210K. So now I'll check. Assume this is my first partition. This is 200K free. 210K can be fit in 200? No, not possible. Next, check the next one. 210 can be possible to fit in 180? No. Check the next one. 210 possible to fit in? Yes, I can fit. So I brought this 210K into what? Say, let us say this process. Let us say this process name is say P1. So I brought P1 into this one. I will not check the next one. See, as soon as we find the free hole which is large enough to hold, so simply I will bring, that's the first fit. That means as soon as I find the first free hole, that means first free hole means not the very first, which is large enough to hold. This is not large enough, this is not large enough. This is the first free hole I find which is large enough to hold this one, so I stop. So this is what the first fit. In the first fit, see, we have not checked this one. As soon as I find I fitted, so here in the first fit is the faster when compared to other two. So the first fit, so it will stop as soon as we find the free hole. Okay, this is what the first fit. Okay, in this example I found. Now, okay, now let us take the same example now. Now let us see what is the best fit. Now, if I must store this P1 into 360, what is the problem? 210K, I am storing in 360, so leftover space is how much? Leftover space is 360 minus 210, 150. 150 kilobyte space is wasted. That means this is occupied only this much. See, this is occupied only this much. See, this remaining 150 KB, this remaining 150 KB is free now. That we are not using. Waste. We are wasting. So leftover space is more. Okay, to overcome this disadvantage, so we go for one more selection criteria called best fit. As the name itself indicates, I will check all the free holes. Out of all the free holes, I will find which is the hole which can fit the program with leftover space is minimum. Whichever the hole whose leftover space is minimum, so that's the best. Okay, that I will fill. Okay, now in this case, I'm not going to fill this in this one. See, I'm not going to see. I check. Next, 210K, not possible to fit. Not possible to fit. Is possible, but I check one more phase. 210, 220. 220, yes, but leftover space is only 10 KB, so this is the best fit. Now here I am bringing the P1, here my leftover space is only 10 KB when compared to the earlier first fit is 150 KB. So this is what the best fit. So in the best fit, we are finding the free hole which can hold large enough to hold the new program with a smaller leftover space. Okay, that's what the best fit. But what is the disadvantage of best fit? In this best fit, now leftover space is only 10 KB. See, sometimes, in most of the programs, we are using static variables, okay, fixed variables. But there are some programs are there in which we are using some dynamic libraries, or we are using some dynamic memory allocation variables. In dynamic memory allocation variables, we don't know how much space we need. So it keeps growing at the runtime. At the runtime, it may be anything. So we need some extra space. Here, in this case, it is not possible. So to overcome that disadvantage, we go for worst fit. In the worst fit, again we check all the what? All the free holes and whichever the largest hole, and that is fit enough, okay, that is able to fit the program with largest free or largest leftover space, that I'll find. Now here I'll find which is the largest free hole, 360. Now here I am storing this P1 in largest hole, that is what the first fit. Okay, so that we should get larger leftover space, like that in the future we can do any enhancement in the code or any number of data we can, whatever we can do enhancement, we can extend. So for that we need some larger leftover space, so we go for the first fit. So now you people understand what do you mean by first fit, best fit, worst fit with this example. Okay, so now the thing, now what is the problem with contiguous memory? Now we discuss contiguous memory allocation, all these things. Whether we are using this concept in our operating system today? No. Today, whatever the operating system we are using, that in order to allocate main memory allocation, we are not using this contiguous memory allocation. We are using another concept of paging. Why we go for paging? Because it is having some disadvantage. What is the disadvantage? The disadvantage of this contiguous memory allocation is called fragmentation. Fragmentation. Now let us see what do you mean by this fragmentation. Okay. Now assume I already said, so these are my what? Free hole. Assume, okay, I will draw the same thing in a little bit larger, so that for you people it is easy for visibility. Assume now I am writing only the user space. Only the user space. I am not writing the kernel space. Only the user space. Assume these are the partition. For example, okay. For example, these are my partition. For example. Okay. So right now I got 1, 2, 3, 4, 5, 6, 7 partitions. Okay. So now assume here I stored what? Say, for example, here I stored PA, process A, and this is of size, say for example, 290 KB, for example 290 KB, this partition. So next I stored, for example, say P3, process P3, and its space is taking say 210 KB, 210 KB. And next I store and assume here I stored, say for example, say PX, and it is having say for example 100 KB, 100 KB. And next I store one more process here. Let us say this is say PB, and it is say for example 350 KB. Okay. Next similarly I have some other program, say for example P1, and it is say for example 520 KB. And I'm doing one more program, say let us say PY, it is say some 280 KB, 280 KB. Okay, and we are having one more process saying that say for example process 4, P4, and it is say for example 120 KB. Now main memory is full now, user space is full. Now after some time I assume I want to bring one more program, but there is no free one. So what to do? Assume any one program is work. Assume after some time I close some application, so I close some files. For example, assume I close this, so okay, I close this, okay, and again I close this, again I close this one. Assume now 1, 2, 3, 3 holes are okay. Assume let us this also, PA also, this are PA also closed, okay, and now 1, 2, 3, 4, okay, these two and these two are free holes. Assume now I want to bring one more program. Let us say that program is say, see right now it is how much KB? 290 KB. Now I want to bring it of size, say 250 KB, and let us say this process is a P1. Now that means now what? So P1, so this much is occupied. Okay, so this is occupied P1. Now how much it is free? Now free is, I'm having free 290 minus 250 is how much? So 40 KB is free now. Here 40 KB is free. Okay, next, after some time I want to bring one more. Assume now in this process 210 kb. In the 210 kb, I brought one more process, say for example PA I brought. Assume this process is say 180 kb and it occupies this 180 kb. It is also occupied and I left over with what 30 kb. 30 kb, 180 kb, this 30 kb, this is not 290 now, okay. So this is what 250 kb, this is 180 kb, okay. So now this is as it is. Assume I brought one more process, for example say PB and it occupies 200 kb. Okay, let us take a 200 kb. So 200 kb means, so this occupies 200 kb. I left with what 150 kb. So this is also occupied. Assume again out of 520 kb, again I brought one more new program, say P5, and this is occupied, say for example 400 kb. Now free is 120 kb. Now if you observe in this, okay, if you observe in this, see now here 40 kb space is free, 40 kb hole. Here 30 kb, here 150 kb, here 120. So now assume I want to bring one more file. Now that assume that new program file size is for example 400 kb. 400 kb. Is it possible to bring? Is it possible to bring? Okay, now let us say, okay, let us take 300. Now I want to bring a new program of say 300 kb. Is it possible to know the occupied? It is free. How much say 120 kb? Not possible. Again, it is occupied, free 150 kb, but it's not possible. Again, occupied. Now it is free 30 kb, not possible. Occupied, free 40 kb, not possible. So that means now I can't, but if you closely observe, I'm having how much now? Here 120 kb, here 120 kb, here 150 kb. Okay, then here I'm having what 30 kb, and again I'm having what 40 kb. So if you add all together, 712, 7714, so 340 kb spaces are all I'm having. So altogether I'm having 340, but I need only 300 kb. Even though space is there, we are not able to allocate. Okay, so this is called fragmentation. That means we are not using the free holes efficiently. That inefficient way of managing the memory space. Even though we are having enough space, we are not able to bring the new program into that. This problem is called fragmentation. Okay, so again this fragmentation is of two types. One is internal fragmentation and another one is external fragmentation. So what do you mean by external fragmentation? See, external fragmentation leaves a small free holes between every two processes. See, between these two occupied holes, I am having one free hole. Again, between these two, again I am having one more hole, free hole. Again, between these two, I am having again one more free hole. Again, between these two processes, one more free hole. But these free holes are very, very small, and in that I cannot bring any new programs. So that is wastage of memory. So that's what the external, that means external to the partition. External to the partitions, we are having some free holes. So what is how to overcome from this? In order to overcome this, what to do? You move all the free holes one side and you move all the occupied hole processes one side, so that I'll get all the free holes one side, and you can merge all those smaller free holes into one larger hole, so that we can bring the new program. So that is how to overcome the external fragmentation. That can be eliminated completely by using the next concept. It's called paging. Okay. So now, what do you mean by internal fragmentation? So now let us take again some example. I'll rewrite this. So suppose again I'm writing some user space. Assume I'm having these partitions. Let us say this is partition, say PA, and this is P1. Okay, and I'm having here, say for example, px, and I'm having here, say pb. Assume the size of this process, size of this hole is, for example, say 40,910 bytes. Okay, and size of this process, for example, say it is a 32,750 bytes, and size of this process PB is, say for example, 45,650 bytes. Okay, so this is something, say let us say this is, say for example, 10,000 bytes, for example. Now assume after some times I freed this, I close this app, I want to bring new one. If I want to bring new one, assume it occupies, that's new file size is, for example, 40,908. If I bring 40,908 here, it occupies, almost occupied new one. See, 40,910, 98. What is left over? Only 2 bytes is left over. Only 2 bytes is left over now. Now, it is the burden or the overhead for the operating system to maintain this smaller size word 2 bytes, in which we cannot do anything. 2 bytes. In the 2 bytes, is it possible to run any program? No way. Similarly, assume this px. It is having 32,750. Assume after some time I brought some other file and it is occupying, say, 32,740, leaving 10k, 10 bytes. Only 10 bytes is free. So like this, now our operating system has to maintain a table in which it has to say free holes, it has to maintain 2 bytes, 10 bytes. If you merge these also, we cannot do anything. So this is called internal fragmentation. Okay, hope you people understood what you mean by contiguous memory allocation, why it is called multiple partition, also called as variable partition, multiple partition method, and then how to allocate the program to the main memory using the concept of best fit, worst fit, and the first fit. Okay, among these three selection criteria, first fit is faster because it is not going to check all, but these two need to check all this. Okay, so they are slower. But if we want to utilize the efficient memory, we go for the best fit. Hence, the name of it is the best. Okay, so it will give very leftover space is very small, whereas worst fit, as the name itself indicates, it will give larger leftover space. It leads to worst. Okay, it leads to inefficient way of managing the memory spaces. Okay, and the major disadvantage of contiguous memory allocation is fragmentation. So fragmentation is nothing but inefficient way of managing the free space. Sometimes even though we have enough space, it is not possible to bring the new program into the main memory because the free holes are not contiguous. So for that, you move all the process one side and free holes another side, and you merge all the free holes into one larger free hole. Okay, this is called compactness. Okay, this concept is called what? Compactness. But it is very difficult. It is not so easy. Implementation wise, it is very difficult. Okay, so hope you people understood this. If you have any question, please write in the comments. Thank you. Thanks for watching.